Hello there, science. This is your Loom Edpuzzle video that you will be watching to complete your notes on plate boundaries. Remember, you do need to watch the entire Edpuzzle. You do need to make sure that you are answering the questions in Edpuzzle in order to get full credit. As well, you need to be filling out these notes. Where's the last part? There it is. You need to be filling out these notes as we are completing the presentation. So let's get into it. All right, so we are going to discuss state plate boundaries. Let's actually go back here. Your topic objective is plate boundaries, and your essential question is how do the tectonic plates move and interact? So over on your notes at the top, plate boundaries, and where the essential question is, how do the tectonic plates move and interact? You can pause the video right now so that you can copy this down. You can go back, but because we are on a video, I'm going to go ahead and move right on into it. So again, plate boundaries is the topic objective, and it is segment 4, scope 4. Remember, anything that is bolded and highlighted in this yellowish color is part of your actual notes and will be used to fill in the blank on the right-hand side. Anything that is bolded or highlighted in purple is your question or cue, and that will go with the bullet points that are on the left-hand side. So let's review. We will be pausing the video at certain points, and you're going to be answering the Edpuzzle. So make sure that you are truly answering. The first is, what is the theory of continental drift? We are going to pause the video right now, so please answer. All right, so you should have answered, what is the theory of continental drift? The theory of continental drift is that the continents were once connected, but over time have drifted apart. Our second question is, what is the evidence for the theory of continental drift? So again, the video is going to pause and you are going to answer that question. All right. And the answer to that is there is the jigsaw. I don't know why the one is in front of it. There's the jigsaw shape, so it looks like a puzzle. There's fossil records that show fossils of one species could be found in South America, but also found in Africa, proving that they were once connected. Mountain ranges appear to be identical on the East Coast as it is to Scotland. And there's also glacier evidence of glaciers in areas where there should have never been a glacier, even during the last ice age. And then, what is the theory of plate tectonics? Again, I'm going to pause and you're going to answer. All right. The theory of plate tectonics is simply that the Earth's crust is divided into very large pieces that move over the mantle. And the mantle is that molten area underneath the Earth that allows it to move, kind of like when you put something on top of Jell-O. All right, so let's get into plate boundaries. How do tectonic plates move? So what is the actual movement happening? We've learned that theory of plate tectonics, but now we're actually going to get into plate tectonics. So this is your first question or cue. Plate boundaries are areas where different plates meet and interact. So we have these gigantic land masses, and they're going to have to meet another. And where they meet is a plate boundary. And these interactions determine what is developed on the Earth's surface and what happens, depending on, do they push against each other? Do they slide against each other? Do they pull apart from each other? All of these interactions have very different outcomes. And there are 3 main types of boundaries that we are going to discuss. If you need to, as we go through, you need to pause this video to take down the notes. I am not going to be pausing. to give you time, you need to pause the video yourself. And I'm sorry that I keep like snorting over here. Like I said, I'm still really congested. All right, so divergent boundaries is your next question or cue. This area is where two plates are moving away from each other. And I'm going to randomly be turning on my camera so you can see the hand movements I'm making. Maybe. We'll see. I do not look good today. I really don't feel like having myself recorded. But this is the area where two plates are moving away from each other. So take your hands and you're going to push away, push apart. You're going to separate. They are diverging. More often than not, this happens under the ocean. We don't see a lot of divergent plates meeting when they're not really meeting, they're pulling apart. We don't see a lot above the Earth's surface where we can visit. Most of this does happen deep in the ocean. And this creates new ocean floor. That's where we get new crust, is from the ocean. We really don't see it happening outside of the ocean. Currently, there actually, though, is a divergent plate boundary that is pulling apart on the continent of Africa. You can go to the Rift Valley in Africa and you can see new Earth crust forming there. And this creates rift valleys and new Earth crust. Now, again, most of the time it does happen under the ocean's surface, but there is one currently happening in Africa. What you are going to do now is in your notes, there's a spot. And let me exit out of the notes. Nope, that's not him. That's not the right thing. Over here in your notes, you'll see right here, there's this open area. You were going to draw this picture right there. Now, you don't need to necessarily label the asthenosphere. You don't necessarily need to label plates. And you don't have to make it look that pretty. Let me draw it and then I'll show you on camera. If you want to label, you can, but you don't necessarily have to. So let me turn my camera back on and show you. I'm hiding my face. All you have to do is draw that. You don't have to make it look fancy. You simply draw that. Oh, that's that background effect. I don't want that. I want to, nope, open the menu, close it. Okay. So you're drawing that in your notes. Boop, boop. All right. Now, under your bullet point that says divergent boundaries, you are simply going to draw two arrows pointing away from each other. So over on your questioner Q, so again, we're going to go out. Over here under this bullet point where you wrote divergent boundaries, you're going to draw two arrows pointing away from each other. Just like that. You see me down here in the video. All right. So here are some examples of divergent boundaries. This is the one actually in Africa right now. This is the valley. This is the rift. And it is actually moving. This is a GIF of how it's actually moving, what is happening. So the plates diverge about 3 to 10 centimeters a year. So it's not substantial. And new crust is created as that magma pushes up and forces the plates apart. And then this one is in Iceland. You can go visit. You are walking right down the middle. This one's no longer active. All right. So let's actually go back. We are going to pause the video here. There's going to be a question or two about divergent boundaries that you need to answer. And then we will move on to convergent boundaries. All right, so convergent boundaries. This is an area where two plates move towards each other. So it's the opposite of divergent. You're converging. This creates mountains and volcanoes, but it can also create other things. It depends on how the boundary pushes. And this is where I'm going to actually turn on my camera. Please don't make fun of me for looking really like a hot mess, guys. Sup. So, when the boundaries push together like this, they're either going to push like that because they have equal density. So they're going to push and create mountains and volcanoes. Or one is going to be more dense than the other. And when that happens, they're going to go like that. It's going to go under. One will subduct, under. It will go under. And those boundaries is when that one bends or slides under the other, and it curves down into the mantle where it gets melted into magma. So there's those two options. You're either going to have them push and they'll bend together up, or one is going to bend under. Bye. All right. So this picture again goes in your notes, and I'm not going to show you this time. You can figure it out yourself. You're going to do convergent plate boundary, and you're going to show them going in. Now this one, I do want you to show the subduction because subduction happens more often than actual like mountains and volcanoes. So divergent plates are how we get new Earth crust. Convergent plates are how we recycle old Earth crust. Because that crust is going down into the asthenosphere, which is where the magma is, it's getting melted and being recycled through the rock cycle. Underneath your bullet point that says convergent, draw 2 arrows, not hours, arrows pointing towards each other. And again, I'm not going to show you the example because you had one for divergent. All right, and here are examples of convergent boundaries. The Himalayas were created because of a convergent boundary. Mount Fuji, which is a volcano, is created by a convergent boundary. So this is where we get mountains when they are equally the same density and they push together and they start to kind of fight for who's strongest, but in reality, they're both strong and they push up, forming a mountain. There is some being pushed down too, just so you guys know. Now here is a subduction. Mountains still get created in these. These are where you see mountain ranges, not just a mountain. If you see a mountain like this, it's a volcano, and it's more than likely going to be just a traditional convergent. When you see mountain ranges getting made, like the Himalayas, you'll see these a lot also near coastal areas. This is where subduction's happening. So let me go back. The oceanic, I can't pause, the GIF. This is where oceanic plates, so those that have mostly ocean above them, converge with continental plates. So there's two types of continental plates, or two types of plates, we have continental and oceanic. This is two continental. A volcano tends to be two continental. When you have an oceanic plate and a continental plate, that's when you tend to get subduction because their densities are very different. The oceanic plate slides under the continental plate. All right. So again, we are going to pause the video. You are going to answer just a few questions, and then we will be back. All right, so transform, we also call them transformative. Convergent boundaries are also called convergence boundaries. As long as it has that root That's what matters. So transform can also be transformative. Convergent can be convergence. So as long as you have like the converge part or the transform part, you're good. So these are transform boundaries, and these are the boundaries you guys are actually more used to because we live on one. Excuse me. This is an area where two plates slide against each other. They do the rubbing. These boundaries create a lot of earthquakes. Now, obviously, volcanic eruptions create earthquakes, they create tsunamis, but if it's just an earthquake by itself, it's more than likely to transform boundaries. And we live near the very big one, the big fault, which is the San Andreas Fault. So you're going to draw the following picture of a transform fault boundary. We also call them, like I said, it's a transformative, a transfer fault boundary. Sometimes it's a transformative fault plate boundary. As long as you know the word transform boundary, you're good. So this is where the plates slide against one another in opposite directions. They don't slide against each other in the same direction. It's opposite directions because it creates a lot of friction, a lot of buildup, and that's what causes the earthquake. So then again, underneath your bullet point that says transform, draw two arrows, one above the other, and you're going to draw them pointing in opposite directions. And I am going to turn on my computer, my camera for this one so you can see. This is what it's going to look like. So you're going to have one arrow going one way, and then on top, another arrow going the other way. Now, here are the examples. This is actually the San Andreas Fault. This is a picture of the San Andreas Fault. Not too far from here, actually. The second picture there is the transformative fault line in New Zealand. That is the one that's been causing a lot of devastation in New Zealand. The big Christchurch earthquake, which happened in 2011, was due to this fault. And that's actually why I didn't get to go to Christchurch when I went to New Zealand, is because the earthquake had just hit. And this is a GIF showing you how it works. Now, the earthquakes don't happen in just one area. They happen all along the fault. It's really just where is the giant buildup of all of that friction and that energy. So again, we're going to pause the video here in just a moment. You were going to answer the questions and then come back to finish the notes. All right. And I am giving a lot of buffer room on the notes just because it's hard for me in a Gillette or Edpuzzle to find the time. All right. So your next question or cue is signs of a plate boundary. How can you tell that there is a plate boundary nearby? Well, there are two distinct ways to see boundaries. Now, yes, you can see them. As you can see from all the pictures, you can see them. But there's other ways we can definitely tell. And these are all the different plates. There are, I believe, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. So there's 11 major plates. And where these plates tend to interact, where we know these fault boundaries are, we see a lot of volcanoes here in the Ring of Fire. You can see it. There's also a ton underneath the ocean in the Atlantic. And this counts as part of the Ring of Fire too, as well as right around the Philippines. And then we also look for the ocean ridges underneath the ocean, which are all right here. We can see these ridges. The Mid-Atlantic Ridge is the most famous one. The Mid-Atlantic Ridge is it's just as popular as like everyone knows the San Andreas Fault here on the West Coast. Everyone on the East Coast knows when you talk about the Mid-Atlantic Ridge what it is. You have the Hawaiian Hotspot, which is a little different because it's not right along a ridge. The Hawaiian hotspot was created from older magma pushing through, but there's also some smaller boundaries that run through. So, for example, I lived kind of right in here growing up, and we had earthquakes. I experienced two earthquakes when I was in middle school. And then I had a very big experience when I was working in college. So the first, actually, no, it was high school and then college. So the first time I experienced an earthquake, I was in high school. I was staying after school for cheer practice, and I was refusing to run because, as you all know, those of you in my like sixth and seventh period who get a lot of stories from me, I did not like my cheer coach, and I refused to run, and I would cut through an area of my school to kind of get out of running. And I was in the hallway, and all of a sudden, all the lockers started popping open, and the building felt like it had been hit by something. And we found out later that there was an earthquake. We have a small fault running through the middle of Virginia. And it turns out that this fault line actually, there's a nuclear power plant sitting right on top of the fault line in Lake Anna in Virginia. So that's fun. That was fun to find out. And then when I was working, I worked at a place called Justice. I think the girls might know Justice. I was working at Justice when I was in college, and I was an assistant manager. And they sent me up to DC for the week to take over and run their store because their manager had quit. So it was my first day. I'm in this Justice. Like, we could see, like, we were very close to the Washington Dulles airport. And again, all of a sudden, the lights started flickering and the building was shaking, and we thought we got hit by a plane, that a plane went down and struck the mall because we were right in the flight path. That was actually a massive earthquake that, again, was from this fault line that ran through Virginia, because Virginia has a lot of mountains that were created by this fault line. We actually had a massive earthquake that damaged the Washington Monument because of their earthquakes can happen anywhere because there are a lot of smaller faults. But the big ones are right here. The big ones. There are smaller ones. So I don't want you guys to sit there and think, oh, like earthquakes can only happen in California or in Japan. No, they happen everywhere. They're just going to be gigantic here because of the massive fault line it sits on. So again, the two distinct ways: location of earthquakes and volcanoes, and ocean ridges. Now, one final thing. The theory that the outer rigid layer, that's the lithosphere, that is that thick crust that we are currently standing on, is divided into several large and smaller plates that move in relation to one another, deal with a lot of energy. How else would they be able to move? You need energy to move. Well, plate movement is driven by that geothermal energy, that radioactive energy from the core of the Earth. Plates do move very slowly. Now, obviously, there could be catastrophic events. That's what volcanic eruptions and earthquakes are. But in general, they are uniformitarianism. They only move 1 to 9 inches, or centimeters, not even inches, 1 to 9 centimeters a year. And if you guys, I don't even know if I can hold it up for you to see. Let me just see here. All right. That's 10 centimeters from there to there. So it only moves a tiny little bit because that's 10 centimeters. Or no, that's 1 centimeter. I can't read. That's 9 centimeters. It still is not a lot. Sorry, I saw the 10. That's 10 millimeters. But it can only move up, 1 to 9. It does not move a lot. It does not move a lot. However, when massive earthquakes happen, it's because there's a lot of buildup of this geothermal energy, and it's going to do a massive move, and it's going to be catastrophic. But generally, the plate movement is uniformitarianism, and it takes a very, the movement of plates to a whole new place is uniformitarianism, because it does take a very long time to move a substantial amount of distance. So we're going to pause the video again here, and you guys are going to answer just a few more questions. I cannot breathe, guys. It's so dusty in this room. And then it's so cold outside but warm in the room. It's messing me up. All right. So you needed to fill out your notes. All right here. You do not do a summary. You are not doing a summary. These notes are going to go, let me just open up the daily agenda here. I'm not going to show you guys, but I just need to open it for me. All right, so these notes are going to go on page 61 of your ISN. So you need to take a moment, look at the daily agenda, and paste these onto 61 the way the daily agenda shows you. I will be checking this when I return from the test that I am taking. So when I return, I will be checking it. So more than likely, I'm going to be checking it on the first. Nope, wrong day. Sorry. This will be checked on the 8th and 9th of February, more than likely. So if you guys have any questions, remember to send me an email. Make sure you've answered all the questions within the Ed Puzzle. Make sure you watch all the way to the very, very end of the video, because if you do not, you will not get credit for it. And I will see you guys when I return. Thanks. Bye.